every time. Okay. Right. So today we are going to be talking about simple population models in discrete time. This material may be familiar to many of you, but I want to make sure, at least in the first few lectures, that everyone's on the same page, so we've all got the same good foundation. So we're going to be starting off by thinking about exponential growth. And today, hopefully by the end of the lecture, you should be familiar with these concepts. So you should understand the concept of discrete time and what that means as opposed to continuous time. We can talk about exponential growth and understand what that is and some common misconceptions about what exponential growth actually means. The idea of a per capita growth rate, what it means to the idea of something that's per capita, and then a linear equation in discrete time. And then using these concepts, you should be able to construct your first simple models in discrete time. So what do I mean when I say discrete time? Well, usually we think about time as being something that's continuous, right? You know, there's no discretization in times. You don't jump between intervals. But when we model them, when we model populations, we don't necessarily have to do things continuously. We're gonna move on to continuous models for most of the course, but we'll be starting off in discrete time. And there are some cases where you might want to make discrete jumps, say from day 1 to day 2, or week 1 to week 2, or year 1 to year 2, or even from generations. There are lots of populations in the natural world that have non-overlapping generations, or they have very tightly synchronized dynamics. And so there are certain cases where discrete models can be of more use. In some contexts, they're also a bit more simple. So there are certain cases where we might care more about discrete time. So the length of this interval, this time period before, between going from, say, day 1 to day 2, day 3, or whatever, or year 1, year 2, and so on, that length of that interval is called the projection interval. Okay. So first question, when are discrete time models most appropriate? So whenever you see these orange questions, this is when I'm usually going to ask you guys something. Okay, so when do you think it's most appropriate to use a discrete time model as opposed to a continuous time model? Yeah, so we're modeling population dynamics sometimes. I mean, sometimes we might want to do it into continuous versus discrete. So any like distinction as to why you might want to have sort of very go from these discrete jumps from one time period to the next, as opposed to modeling things as being continuous. Think about different biological processes that you might have. Oh, that's not a good sign. I think that's my iPad going off. That's what that is. Okay. Think about, you know, what types of biological processes do populations go on in populations? So you mentioned population dynamics. So what kinds of things affect population dynamics? Disease, yeah. How do populations grow? So there's births. What else happens to populations? What individuals in populations? Yeah, exactly. Yeah. So there are births, there are deaths. And in some populations, like humans, these things occur continuously throughout the year, right? There's no fixed pattern. There's a bit of variation where there are peaks and troughs. But in some species, there are very tight, short mating seasons, right? So in species that have very short mating windows, or if they have sort of big death events, you know, suppose they all die in the winter, and then the next year the population grows again from, say, seeds in various plant populations. There's a very discretized interval and things are synchronized. And so in those kinds of populations, you may care more about modeling things in discrete time. So when might you care about these things? Yeah, it is working. So if you've got well synchronized populations, to abbreviate that. So for example, short mating season. Also, sometimes if you're maybe fitting to certain data, you might care about these discrete time models more if populations are censused at very fixed time intervals, right? So fixed interval census. They're also very easy to solve. As a very first like population model, if you want to, you could just put this down in Excel, or you could have a table, as we'll do later in this lecture, and just drag and drop, project forward on like a spreadsheet. So they're very, very simple things to work with. Okay, so let's think about how do we construct our first simple population models in discrete time. So suppose we have a population size or density. I'll be using these terms interchangeably, size and density. Technically, individuals in a population, they are going to be whole individuals. So you would usually think of there being however many, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 people in the room or whatever. But usually these values of nt here, they'll be continuous. Okay, so they can take any positive real value or non-negative real value. They could be 0. So that's why we refer to them usually as a density. A population density is more correct. And you can think of that as number of individuals per unit area or volume. Okay, but if it's easier to think about it, think of it as size, and then you can think about the area. Okay, so we have our population size or density of time t is n sub t. Here's our time unit, and that time unit could be, like I said, days, weeks, months, years, generations. So we're also going to assume that our population at the next time point, t plus 1, is going to be completely determined by the population size at time t. So why does this matter? Well, this means that our model is deterministic. So this means no random effects. Those random effects can also be referred to as stochasticity. So that's basically just saying that if I start with the same initial conditions, the same initial population size, I run it through my model, I will always get the same pattern coming out of it. Okay. If I had a model that had some stochasticity, some random effects in it, if I was running like a simulation on a computer and I added some randomness in here, then I would get a different population size. Okay, so everything is completely determined. So what does this model look like if we have a very simple population model? One way of visualizing this is thinking of our population at time t. And then we're projecting forward to our population at time t plus 1. Okay, and what does that look like? Well, we have some processes, say things like we're going to be adding on births, and we're going to be taking away deaths. So sometimes when you're like putting together a model, it helps to come up with like a little sketch of it. Another way you might want to do this, or you might see it, is just think of our population n or nt, and you can think about births as things that go around and add in to this population. So this would be births. So we're adding births in. And then an arrow that just leaves and goes to nowhere, which is deaths. Okay. So sometimes in a textbook, you might see them drawn up as schematics that look a little bit like this. Okay, so what does the general form of this type of model look like? So if we have a single species, single population, we're going to assume a few things about it, like that population is homogeneous, which means there's no variation that we care about within that population. So we're not, say, distinguishing between males and females or individuals of different ages. So it's very simple population. You can think of this as maybe being, I mean, it's good for even human populations, but you could think of something as like bacteria in a petri dish, which they're all very similar, okay? So we use something called a difference equation or a recursion equation. Who's heard of difference and recursion equations before? Anyone? No? Okay. Okay, one person at the back, good. Okay, so we write this down as the population, n, at time t plus 1 is going to be some function f of nt, where nt is our current population size. So you refer to this f of nt, this little f, as the net growth rate. Okay. So is a net growth rate because we're going to have things that are adding to the population, like births or migration in, and things that are being taken away, like deaths and migration. Okay, so that's the net growth of the population of size n. And we're going to say that this function here is going to be non-negative, okay? If it was negative, then we'd suddenly have a negative population size in the next year, okay? We're also going to assume that we can't just generate individuals out of nowhere. So for this, we're going to assume there's no migration. If we have no individuals in the population, there's going to be nothing changing, okay? We can also write this usually as NT, so our current population size, times by capital F of NT. So little f and capital F are different functions. And this capital F is the net per capita growth rate of population. Again, this is non-negative. And so little f of n is the net growth rate of the whole population, and big F is the per capita. So per capita essentially means per individual in the population. So for every individual within this n, they each produce capital F of n, on average, surviving individuals at the next time step. If you ever have any questions, just raise your hands, by the way. So like I said, this is a per capita essentially means per individual. And this capital F of n is essentially the net number of individuals produced. So bear in mind when I say produce, that means individuals that are surviving to the next time step. So they might produce 5 offspring, but 3 of them might die, and they might die as well, in which case you would be subtracting 4 from that 5. Okay, so it's all about what is surviving to the next time step. Another thing to think about is that we often refer to both of these functions as rates. They are in fact dimensionless. And what I mean by that is they're just numbers. Okay, so a rate is something like speed or distance. It has a unit. These little fn and big Fn, we refer to them as rates because just convention really, but they are in fact dimensionless. So sometimes in textbooks, you might see them referred to as ratios or net production and net per capita production, okay? That's just a terminology thing to let you know that you might see it written down as something slightly different. Okay, so let's construct our first simple linear model. So remember, we're going to have our NT plus 1 is going to equal the net growth rate. And we can split this down into what was the population before, present population. I'll do my highlighting a bit, they say. This is my present population. And then we're going to think about the change of delta NT. So we've got our current population and some change, and this change could be positive or negative. And here, this change is going to be adding on our births and subtracting our deaths. So this change is really both of these things here. And in this simple linear model, we're just going to say that we have a per capita death rate B and a per capita death rate D. So each individual has a probability of dying D and produces a total number of individuals B. So then what's our net per capita growth rate? Well, remember that we had our NT plus 1, our time population at the next time, is our net growth rate, or we can write this as NT times our net per capita growth rate. So if we just take, if I go back to the slide here, you notice here we've got NT here, an NT here, an NT here, and an NT here. So we could write this as NT times by 1 plus B minus D. So that means our F here, our capital F, our net per capita growth rate, is just going to be that thing that was in the brackets, 1 plus B minus D. I'm going to call this lambda. So just to recap there, that B is the average number of surviving offspring per individual. So it's not necessarily the number of offspring. As I mentioned, some of those offspring might die. It's the number of surviving offspring. You think about, I don't know, say frogs producing tadpoles, or they produce eggs that then lead to tadpoles, right? Lots of those don't survive. Okay, so we'll be accounting for that, that loss in that B term. D is the probability that a given individual dies during the year. I say year, this could be any time interval that we're talking about. And so we refer to this lambda then, which takes into account all of these things, as the net growth ratio, or the net growth rate. And this should be a per capita here, net per capita growth ratio. Okay, so these parameters here that we've introduced, this B, this D, and this lambda, do they have units or are they dimensionless? Can I have a show of hands of who thinks they have units? Who thinks they're dimensionless? And who's not sure? That's fine. So they are in fact dimensionless. And the reason being that B is just a number and D is a probability. For them to, yeah?
If lambda is less than 1, is it still called like growth ratio, or
That's a very good question. It is. It's just a negative, well, it's a negative growth if you like. Yeah. But it's a very good question. Yeah, I'll be talking usually about things like exponential growth and population growth, just because it's easier to talk about that rather than exponential growth / decay and so on. But yeah, exactly. It's still called growth, but truly it's negative growth. So for these to be rates, they would need to have some sort of units. They would need to be average number of surviving individuals per offspring. Sorry, number of surviving offspring per individual per. I mean, they are per unit time, but it's the time we've factored out essentially. Okay, so in a continuous time model, they can be rates. In discrete time, usually they are just going to be dimensionless. Okay, what about biologically realistic ranges for these parameters? So something that we'll often be talking about is what is biologically realistic for our models? What I mean by that is this up here is just a mathematical equation, right? The math doesn't know that B can't be negative, say, right? The model could do whatever we wanted to. We have to constrain our mathematical model to something that is biologically realistic. So what are some biologically realistic ranges for these parameters? So for example, I'll give you B, average number of surviving offspring. Well, this can't be negative, right? It has to be at least 0. But it could take any value above that, right? How about D? Any ideas? Yeah.
Between 0 and 1.
Yeah. Between 0 and 1. Technically inclusive, because everything could, it would be a very trivial model if everything just died out, but in principle that could happen. So it's a probability, so it has to be constrained between 0 and 1. And therefore, lambda. What's the constraint on lambda? Sorry? No, not less than 1. Anyone else?
Greater than 0.
Greater than or equal to 0. Yeah. This is because B can take any positive value. So for example, B could be 1,000. So this could be anything that is non-negative. Okay, so whenever constructing a model, it's always good to think about what are the constraints that we have on that model. Okay, so the model that we've constructed here, we can write in this form, nt plus 1 is equal to lambda times nt, right? Where lambda is our net per capita growth rate or growth ratio. And here we say that the population growth is density independent because this capital F of n doesn't contain any terms that depend on the population size. So it doesn't matter how many individuals I've got in the population, the net per capita growth rate is always this constant lambda. So whether I've got one individual or 1,000 individuals, it doesn't matter. Each individual is producing, on average, lambda new individuals that survive into the next time step. So this is why we have a linear difference equation, because this lambda here is a constant. And so if we want to work out what the solution to this is at any particular time point with some initial condition at time 0, well, let's think about time 1. Time 1, n1 is going to equal lambda times n0. Time step 2 is going to be lambda times n1. But we know that n1 is just lambda times n0. So this is going to be lambda squared times n0. And you can keep doing this again for n3, n4, and so on. So we don't need to work out what happens at all of those intermediate time steps. We just need to have our initial condition, we have our net growth rate, and we just take it to the power of however many time steps we're using. Okay, so our population at time t, n sub t, is going to be this net growth rate lambda to the power of t times by our initial condition n0. Okay. Question for you guys. Maybe chat to the person next to you or think to yourself for a minute. When does the population grow and when does it decay? Have a think about, based on this equation here, the values of lambda. When is this going to grow and when is it going to decay? Have a chat for a minute and then. Okay, any ideas? When does the population grow?
Lambda greater than 1.
Okay, and why is that the case?
You multiply with lambda by itself over and over again.
Okay, and what's
Want lambda greater than 1 to actually increase the number. If it was equal to 1, it would stay the same. If it was less than 1, it would just keep increasing.
exactly, yeah. So if lambda is greater than 1, then we're multiplying something bigger than 1 by itself over and over and over again. So it's compounding. It's like interest compounding in a bank account, right? It's going to grow. And if it's less than 1, then it's going to be decaying. If we have, like I said, 1 to the power of t, then it's just going to stay that forever. So one of the good ways in working out things like thresholds, if you've got something that you know is either going to grow or decay, is to find what that threshold is. And then you know that when you're on one side of that, it's going to have one behavior, and on the other side, it's going to have a different behavior. Okay, so biologically, what does this mean then? Well, each individual has to be producing at least more than one surviving individual in the next generation for it to grow. So that kind of makes sense, right? Hopefully it makes sense. So just to clarify here, for growth, we need lambda greater than 1. And for decay, we need lambda to be less than 1. Lambda still has to be non-negative though. So in this top case, lambda t tends to infinity as t tends towards infinity. And here we have lambda t tends towards 0 as t tends towards infinity. We also have that case where lambda equals 1, everything stays the same. So we stay at our initial condition for all t. Nothing happens. It's kind of boring. So we refer to this is geometric growth technically, but we can rearrange this into an exponential form. And it's analogous to when we have continuous time models that have exponential growth. So we refer to this as exponential usually. Okay, a little exercise for you guys. If my screen will move, which doesn't seem to want to do. There we go. When you guys have a practice of using this model and thinking about how a population grows. So here we've got a population of rabbits containing 100 individuals initially. Each rabbit produces 1.5 surviving offspring on average and has a 50% chance of dying each year. So write down what this model is. We're going to use this linear model that we've just been using now. So write down what your B is, your D is, your lambda, and your N0. And then I suggest having a little table like this, we have your time and your NT, and then have a go at sketching what this graph looks like. Okay, let's see how you guys got on. Can anyone tell me what the value of B is? 1.5, yeah, so we can write that as just 3/2. D, 0.5 or half. And so lambda, 2. Yeah, so we have 1 plus 1.5 minus 1/2 gives us 2. So our formula for nt plus 1 is just going to be lambda to the t. We have 2 per t. And our n0 is 100. So what we're doing each time is we're just doubling. So we go from 100, 200, 400, 800, 1600, 3200. So we can sketch that as being something that looks like this. 8 is about there. This will probably be a bit of a shoddy attempt. Let's do it like this. Who got something that looked like that? Yeah. Okay. So this is your classic exponential growth curve. You see this in lots of cases. So this is a population model of rabbits. You'll see this in the early stages of an epidemic. In fact, the self-study question, these lecture notes is related to COVID-19 and why timing of lockdowns was important based on what we know about exponential growth. One of the common misconceptions, and was really frustrating during the pandemic, was that people confuse exponential for fast. Okay, people, like this idea that something is growing exponentially means they use it in place of meaning something that's going fast. Okay, exponential doesn't mean fast. So typically you might see like, oh, up here, exponential growth, this is a problem. But down here, this is fine, right? Because it's growing slowly here and it's growing fast up here. And so this is a problem during the pandemic that you'd see often people saying, oh, but the numbers are low, it doesn't matter. What matters with exponential growth is there's a doubling time. Okay, here we've got it very simply that each time step there's a doubling time. But it doesn't matter whether it's, in the case of a disease, if it's in 1 week or 10 weeks in some sense, eventually, if there's a doubling time, things are going to run out of control. So at times in the pandemic, people would ask, like, what do I think of what's going on with the numbers? In some sense, if there were 1,000 people infected, and this week, but there were 2,000 infected last week, that's a better situation in some ways than there being 100 individuals infected last week and 200 this week, right? Because in one of them it's going up and one of them it's going down. So understanding like the direction of travel and whether there's a doubling time is key, as opposed to just the rate at which it's increasing at a given moment in time. Okay, let's think about exponential decay. So I had a question earlier about are these population growth, we always refer to as a growth rate? What happens if we have something that's decaying now? So for example, if we've got a bacterial colony, here we've got initially 1 billion cells. So that's 10 to the 9, in case you're not sure what 1 billion is. And we administer an antibiotic, and that prevents cell division and kills 90% of cells each hour. Okay, so what we want to do now is sketch the population size for the first 5 hours. So just like the one before, now we think about what our lambda is. Here our n0 is going to be 10 to the 9. And then just as before, write down your values here in a table and then have a go at sketching it. While a few people are still sketching that, we'll just start working through it, okay? So can anyone tell me what my value of lambda is here? 0.1. Yep. Or 1 over 10. So nt is going to be 1 over 10 power of t. That's my n0. So we started with 10 to the 9 individuals, 10 to the 9 cells. What do we have at time 1? Time 2? Okay. Pretty simple. 10 to the 6, 10 to the 5, 10 to the 4. Okay, so what happens then when we sketch this? We've got 10 to the 9, 10 to the 8, 10 to the 7, 10 to the 6, 10 to the 5, 10 to the 4. What do you notice about that definitely very well sketched red line?
Straight.
It's a straight line. But I thought we were talking about exponential growth, right? Exponential growth is, or exponential decay is, has this thing, there's a doubling effect, right? Things shouldn't look linear. Why does this look linear? Right. So when we have things on a log scale, the reason we often use log scale is because when we have exponential growth or exponential decay, everything looks straight. This is really handy when you're say in experiments and you have some data and you want to plot that data, and then you can just fit a straight line to those data on a log scale. And if you're able to fit a straight line, that tells you you've got exponential growth or decay. So log transforming things can be really powerful for when we're dealing with exponential growth or decay. If you did this on a linear scale, it'd be very hard to see with these huge population sizes, but it would look something like this on a linear scale. Okay, so let's think about like why this is a good or a bad model. Can anyone tell me what a major problem with this model is? This idea of an exponential growth model. Yeah.
There's nothing like limiting it, so it'll just keep growing.
Exactly, yeah. So if we think about what happens if lambda is greater than 1, then n of t, our population side, is going to tend towards infinity as t tends towards infinity. So if this was bacterial cells, they would fill up the entire universe and keep going. Like, this is obviously not a great model over the long time, like over a long period of time. Over a short period of time, it can be pretty good. You know, if you only care about growth in a petri dish for a few days, or you're just trying to model over, you know, human population growth over the last 200 years, it can be pretty good. Do you have a question?
Yeah. I was wondering if like always changing the E and D to get lambda would be better.
Yep. So that's exactly, you've already answered my next question. So how might we improve this? Well, if we think here we have lambda as a constant. So lambda is equal to 1 plus b minus d. Okay, so one thing we could do instead is to make lambda change to something where lambda is density dependent. So remember, I referred to this lambda as being density independent because it was constant. If instead we have something that's more like this, so b is a function of n, and maybe d is a function of n. So our birth and our death rates depend on the number of individuals. Therefore, our net per capita growth rate depends on population size. So this is where we get our logistic growth model, which we'll talk about next time. And in fact, almost all models will have some form of density dependence in. Can anyone tell me why you might get some density dependence? Yep.
Like maybe resource competition.
Yep. So we have competition for resources. It could be competition for space. I mean, space can essentially be treated like a resource. Competition for mates as well. There are lots of different reasons as to why this might change with population size, and generally we would expect it to decrease and potentially go negative as population size gets very large. Okay. I did set this as a self-study problem, but you can start it now if you want, or you're also free to leave. I thought I would apply this idea of exponential growth to think a little bit more about how different countries approach the ideas of lockdowns during the pandemic. So if you think all the way back to February, March 2020, right at the start of the pandemic, which feels like it was about 10 years ago, but it's obviously not that long ago. So many countries delayed going into lockdown until their cases rose to a certain level, right? So this idea of, oh, there's only 100 cases, we don't really want to lock down until things get out of control. There's a problem with that if everything keeps doubling, because eventually things are going to get out of control. And there's also an issue in terms of there's a delay typically to you enact some policies, and then the effects of those policies might be felt for a while, right? So there's a time lag. So if we think about delayed action in an epidemic, suppose in this very simple example, in week 1, we've got 1,000 deaths from infection. So now, rather than modeling population sizes or even infected number of individuals, we're just going to model the number of deaths that's increasing. And we're going to suppose that new deaths are doubling every week. And we're going to suppose also that a lockdown will prevent all new infections, but those who have already been infected take 3 weeks to die. So lockdown is perfect at stopping future infections, but when lockdown is enacted, the deaths will keep increasing, okay? Because they'll be based on people who are infected up to 3 weeks ago. So question is, what is the effect on total deaths if we just delay lockdown from the end of week 2 to the end of week 3? Have a go at sketching a table. Right, so what will that look like? You can have a table that looks something like this. Your week, and you've got 2 scenarios. So you've got what happens if you've got lockdown in week 2, or lockdown in week 3. We can think about, in each of these cases, what's our NT here? Remember, N is the number of deaths. And we can also think about cumulative number of deaths. So I'll put everything on here. So we have 1,000 individuals who die in week 1. And here our lambda is equal to 2. Just because there's only a couple of minutes left. Like I said, this was set up as a self-study, but I think it's good to go through together. Maybe we will work through the rest of this together. So let's work through this one here, lockdown in week 2. So we have 1,000 deaths in week 1. Everyone together, how many deaths in week 2? 2,000. Then 4,000. We've enacted our lockdown here, right? But the deaths are going to keep doubling for 3 weeks, because everyone who was infected in week 2 doesn't die until week 5. Okay, so then we have 4,000, 8,000, 16,000. How about in week 6? 0, right? Because we said our lockdown was perfect, so we get no new deaths. Okay, so we can think about what's the total death count, right? So we just add these up. So we go 1,000, 3,000, 7,000. So we're just adding everything from the column on the left. 15,000, and then 31,000. And then this doesn't change anymore. So that's if we have a lockdown in week 2. We feel the effects down here. Let's do the same thing, but with a lockdown in week 3. So it's going to follow the same pattern to start with, right? 2,000, 4,000, 8,000, 16,000. What goes next? 32,000. What goes next? 0. Right. So this time we had our lockdown here, and the effect happened here. So what's the cumulative going to look like? Well, it's going to follow the same pattern again. To start with, 15,000, 31,000, and then here, 63,000. So the big difference here, right, is that delaying lockdown by 1 week more than doubled the death count. And this was exactly the problem at the start of the pandemic. Countries like the UK, because that's where I was during the pandemic, they saw what was going on in other countries, and then they delayed lockdown. And because of that, it meant that the wave ended up getting a lot bigger, and we had a lot more deaths than we could have avoided. Obviously, this is a very, very simple model, but just illustrates the importance of when you've got exponential growth, the best time to act is yesterday or the week before, right? As soon as you can, and there's no point in waiting. Okay, that's it for today. On Monday, we are going to be talking about logistic growth. Hope you have a good weekend.